Hey everyone, we're here for our next session, which is with Celo on why are the bridges burning? And I'll let James take it from here.
Hey everyone, I'm James Prestwich. I'm going to be talking about why are the bridges burning. We've seen a bunch of bridge-related hacks in the last couple of months. Turns out these things are actually pretty complex and hard to build. So we're going to talk about, what is a bridge, how do they work, and why, a couple case studies on why they're falling apart. So, like I said, I'm James. I'm a protocol engineer at C where I work on cross-chain communication systems. My team works on optics, which is a cross-domain communication standard for EVM chains, broadly analogous to like IBC or other cross-chain standards. Whoops, there we go. The goals of this talk are to get an intuitive understanding of what a bridge is and why it exists, to talk about cross-chain communication, and then to talk about layers, layer violations that lead to bridges falling down, breaking, and losing tons of money. Right. If you've seen me give talks previously, the first couple sections will feel pretty familiar. I tend to go over the basics before diving in deep on things. All right. So throughout the talk, I'll be using standard flowcharts. The rounded rectangles are start and end. The squared off rectangles are process steps. Diamonds are decisions. And the parallelograms are input-output. If there's only one wire coming out of a decision, the alternative is that everything falls apart and you do not communicate between chains today. Typically, that means that we're neglecting all the failure cases in these charts. Cool. So let's start with what a bridge is. Most of us kind of understand that we have Bitcoin or we have Ether and we want to use it in dApps. And unfortunately, those things aren't always in the same place. Maybe we're trying to take Bitcoin over to Compound to collateralize a loan. Maybe we're trying to take Ether to BSC to put it in PancakeSwap or something. So the problem statement is basically, we have assets on one chain and we have dApps on another chain, and we want to go use those dApps. The generalized problem statement is that there's some information on chain A, and we want to get that information to chain B for some reason. Usually this is a balance. We want to move our asset balance over. Sometimes it's like the collateralization status of a CDP or something like that. We want to be able to communicate some property of chain A to chain B. The idea here is that we're going to lock up our Ether. It's going to cross this boundary between chains, and we're going to mint some sort of wrapped Ether on the other chain that we can use in dApps. And when we want to come back, we're going to do the exact opposite. We're going to burn our WETH, and we're going to unlock, cross the divide between chains, communicate to Ethereum that the WETH was burned, and unlock our Ether on Ethereum. And so what makes this a bridge? There's two parts we care about here, right? It's the minting and the burning. We want to ensure that the supply of Ether stays constant and that we're just reallocating existing Ether. And we want to make sure that we only mint if there's locked Ether, and we only unlock Ether if we burn WETH. So the part that makes it a bridge is the application layer. It's the high level, what does the user want out of it? They want to move assets around. But the actual difficult part is crossing that boundary between chains. Ethereum and Celo don't know anything about each other, so how do we get that information between chains? So we're going to introduce some communication channels. There are lots of ways that these can work, but the limitation is that they're all one way. You can't build a two-way communication channel between chains. You need to use two one-way channels to achieve this, which means that bridges are what we call dual simplex. We have two one-way channels. We have a communication from Ethereum to Celo. We have communication from Celo to Ethereum, and those are entirely separate things. So they use two independent one-way communication channels. And duplex channels, a two-way channel, is impossible. We just kind of simulate it using two one-way channels. So I want to dive into a little bit more about how the channels work. Talk a little bit about design constraints and trust boundaries. So we've established that we're doing one-way communication. We got to get info from Ethereum to Celo, and then a completely separate system gets info from Celo to Ethereum. So we wish that you could just on Ethereum send some message to Celo, and it would just get there, and the smart contract on Celo would just process it. Unfortunately, we have these trust boundaries between chains. We can't just send a message across chains. There's blockchains kind of suck that way. They're super passive, and you just can't do it. So we got to start introducing additional systems to help the message get from chain A to chain B, to get from Ethereum to Celo or to Binance or wherever you want to send your money. So dApps can't just receive messages, they can only receive transactions on chain B, which means that we need to introduce some transaction dispatch. So how about we just have Ethereum sign and send a Celo transaction? Well, unfortunately, you can't have Ethereum sign a Celo transaction. Ethereum doesn't have a Celo private key, and it doesn't have a Celo balance, and it doesn't have access to the Celo protocol, the network. It can't just dial up an RPC node and send a transaction. So we need to figure out some way around that too. The core idea here is that chains can only affect what's internal to themselves. They can affect their smart contract state, they can affect their balances, they can log events, but they can't reach outside of themselves to other chains or to other systems. So we need to introduce some off-chain actors. We're going to have Ethereum commit the message to its state or to an event or to some other Ethereum thing. Some off-chain actor, we usually call them relayers, is going to see that message. It's going to decide to forward it to Celo. It's going to create a Celo transaction using its own keys and Celo balance, and it's going to dispatch that transaction to the Celo chain. So we've gone from just, we want Ethereum to talk to Celo, and now we're at, Ethereum talks to Ethereum, some off-chain guy sees that and decides that Celo needs to hear about it and signs and submits the transaction. It's kind of a pain. And there's a lot of complexity and variability. How does the off-chain actor know that Celo should process this transaction? And how does the off-chain actor know that if it spends Celo to get that transaction processed, that it's going to get its money back or it's going to be financially worth it? And how do we build out all of the off-chain software to make this reliable, fast, and safe? This is the entire project of IBC and these multi-year huge infrastructure things, is to make these off-chain actors and the on-chain components reliable, fast, safe. The Cosmos team has done an amazing job of this. Polkadot is just starting with XCMP, and it's incredibly complex and annoying because chains are passive. They can't reach outside themselves. They can only update their own state. But communication has to be active. We need these active off-chain parties that are forwarding messages between chains. So I'm going to gloss over all of the mechanisms that we use to build these communication channels and dive into the fun stuff right about now. In terms of how these work, we have header relays, we have trusted federations, we have validator federations, we have locally verified things like optics, we have one-way header relays like TBTC, There are so many like choices of how to build these. They're all complex and interesting, but I think we're here to talk about why bridges are burning. All right, so we sort all of these bridges by kind of their trust model. Whether it is a header relay, which means you're actually doing the consensus work for the remote chain, or whether it's trusted, whether there's like an oracle reporting on the remote chain. All of the bridges that we're going to talk about today use the trusted communication mechanisms. There is some outside party or set of parties that is moving messages between chains and is trusted by the system. So bridges break when these trusted parties break down in a meaningful way. So that would be the off-chain actors here are trusted. There is no way for the chain to check that they are behaving correctly. The chain simply processes whatever they say to do. The first one I want to talk about is Thorchain. So this was a month or two ago. Thorchain lost a relatively small amount of money. It's just like $8 million. In blockchain terms, that's just like not very much. And the way this happened was tricking the Thorchain custodians into sending Ethereum over the bridge, to sending Ether on the remote chain, even though it hadn't gotten any Ether on Ethereum. So how did Thorchain break? It's this part. It's the part where Ethereum commits the message and the off-chain actor sees the message. In this case, the Thorchain validator set saw a message that was never actually committed. The attacker was able to fool the trusted custodians into sending money even though they hadn't been given the Ether. And to understand how, we need to dive a little bit into Ethereum transaction processing semantics. So I'm going to give a quick overview of Ethereum, of the EVM real quick. So when Ethereum processes a transaction, it always starts with some off-chain user. You sign in your MetaMask wallet whatever transaction you want to make. And you're going to call some smart contract, and you're going to send it some value and some data. You're going to send your smart contract some value and some data, and it's going to process that. It might call another smart contract. It might send on some amount of value, some Ether, and some data. And smart contract 2 might call smart contract 3. So smart contract 2 is going to send smart contract 3 some value and some data. And smart contract 3 is going to do whatever it wants with that. Once it's done, it's going to maybe fire an event. Like it might be an ERC20 transfer event. Events in Ethereum are just something that the smart contract wants off-chain people to know about. Asset transfers, lifecycle events, anything that some user needs to know or some UI needs to know can be logged out in an event. So after it logs the event, smart contract 3 might return some data to smart contract 2, which keeps running. And when smart contract 2 is done, it returns data back to smart contract 1, which keeps running. And then when that's done, it returns data back to the user. So you get kind of this call stack where contracts are calling each other. We're pushing contracts onto the stack, and they run until they're done. They can do anything they want. They can call other contracts. They can update their own state. They can log events. It gets pretty complicated in practice, but it's all transparent to the user. You don't really need to worry about this most of the time. So what happened with Thorchain? As the off-chain actor, they need to inspect this call stack from an actual transaction, which may have, dozens or hundreds of calls in it. And they need to determine how much Ether was sent over the Thorchain bridge. So the Thorchain validators, the stakers running the Thorchain nodes, need to look at this transaction, parse it, figure out what happened, how much money was sent, and what they're supposed to do on Thorchain. Okay, so what actually happened with Thorchain is that the user sent value to a malicious contract, and the malicious contract forward on 0 value to Thorchain. Smart contract 3 here should be the Thorchain router. Looks like I messed up my slides a little. So the user sent value in the top level transaction. So if you look at the transaction on Etherscan, you'll see Ether being sent. But it sent it to a contract that the user controlled and owned, which held on to that value and then returned it to the user at the end of the transaction. You remember that the malicious contract keeps running after all of the other smart contract calls have resolved. So after everything else about the transaction is done, it sends the value back to the user. So once we get to the Thorchain router, it logged out this event saying that it had gotten 0 Ether. And that's what the Thorchain validators were looking for. So the Thorchain validators actually saw this event that says there was 0 money sent across the bridge and you should do nothing. But then the Thorchain validators, because of a bug in how they parse Ethereum transactions and events, took that 0 value event, looked up the transaction, saw that there was value in the transaction, that the user had sent value, had sent Ether to a contract, and said, oh, well, let's override the 0 value with whatever Ether the user sent to their smart contract. So a bug in Ethereum call stack, parsing from the Thorchain validators overwrote the correct value, 0, with the incorrect value, a bunch of Ether, and caused the Thorchain validators to issue Ether to send Ether over the bridge, even though it had never been received by the Thorchain router. So what are the takeaways here, right? Is Thorchain broke in the commitment being correct, but the off-chain actors seeing the incorrect thing due to a software bug off-chain. Like 700 lines deep in a big old Go file that parses Ethereum transactions. So the takeaways here are that chain VMs are hard and taste bad. If you are implementing EVM-specific logic in your bridge, that logic is going to be prone to errors. The EVM is stupid complicated and makes no sense half the time. And if you have to try to parse the EVM and do a transaction trace of all these smart contract calls, odds are you're just going to mess it up. So chain-specific logic should be on-chain, not off-chain. And if Thorchain had the chain-specific logic on-chain, it wouldn't have broken this way. If they had listened to their smart contract instead of doing the additional transaction parsing, they would not have lost $8 million. So, the takeaway here is keep chain-specific logic on-chain. If you're doing something that's EVM-specific, do it in Solidity in the smart contract that runs on Ethereum. Okay, the next one I want to talk about is Polymarket. But first, I'm going to do the disclaimer that I meant to do before Thorchain. I'm trying to give you an intuitive understanding of how these hacks worked. Not all of the technical details are going to be 100% accurate. The narrative is going to be correct. You can dive into these hacks, and there are really great postmortems if you want to learn, flow by blow how it all worked and what lines of code were affected. You should definitely do that. But it's too much to cover in a 30-minute talk. Even getting into Ethereum call stack semantics is kind of a lot and glossed over everything. Anyway, Moving on to Polymarket. Polymarket lost $600 million. There was drama, a bunch of it got returned. There was all of these input data messaging back and forth between the team and the hacker. There was threats. There was, it was great. It was so much fun to watch. How did Poly Network, shoot, I keep saying Poly Market, which is a completely different thing. My apologies to the Poly Market team. How did Poly Network break? Poly Network actually broke in the on-chain message processing. This is interesting because the way Polymarket broke actually had nothing to do with the cross-chain communication. That all worked fine. The trusted Oracle signed the trusted Oracle message, and it was the correct message, and they didn't, try to steal anything. What broke was the message handling. Is when Ethereum received this message from Poly Network, it handled it. The message handling code broke, and we're going to talk about why by talking about how Poly Network processes an incoming message. So we have this incoming cross-chain message. It says, what is the smart contract it's supposed to go to on Ethereum? What data should be given to that smart contract? How much value should be sent to that smart contract, et cetera, et cetera. This is signed by the Poly Network Oracle. So essentially just, some guy out there is signing this. That guy hasn't tried to steal anything yet, but, it's just running on a node in some computer in the cloud somewhere. Signs this incoming cross-domain message, sends it in an Ethereum transaction to Ethereum, and gives it to the Poly Network system. The Poly Network system is responsible for decoding this, sending the data and the value to the recipient smart contract, and letting the recipient smart contract process that however it wants to. So if the recipient is a bridge, mint and burn new tokens. If the recipient is a dApp, do whatever, lending or swap thing. The key thing to understand here is that Poly Network messages can be completely arbitrary. They can have any data. They can call any contract. So the attacker realized that he could call any contract. So he substituted the recipient for the Poly Network bank. And he sent a withdrawal command to the Poly Network vault where all of the money that was sent across the bridge was stored. And the cool thing that broke here is that the Poly Network vault is very tightly access controlled. It has specific administrator that's the only thing allowed to access the money. And that administrator is the Poly Network system. So when the attacker sent a message over between chains, that message was handled by the system and forwarded to the bank. The bank sees a message coming in from the system contract and says, oh, this message is from an administrator on the bank. So I'm going to go ahead and just send all the funds wherever the administrator wants them to go. So what the attacker did was use the message handling logic in the system to spoof admin credentials on the treasury. The treasury was just looking for a message from the system, and the attacker was able to cause the system to send a message because the system can send messages to arbitrary contracts. So the give me all the money instruction from the system to the bank caused all of the money to be sent to the attacker. So the issue here is that cross-domain communications need strict layers. There needs to be a very strict separation between the communication channel and messages coming over it and the local system. Poly Network conflated the communication and the local stuff, and this allowed a message coming in over the wire to steal admin credentials. to use the system to get admin access to the bank, the system should have prevented this by making a separation, a layer, app logic versus channel logic. The way these are typically done, like in practice, is a handler interface, is force the recipient contract to expose a specific interface that is explicitly for cross-domain messages. This way, the recipient contract knows that the system will never send a cross-domain message to any privileged function. The system should only send it to the specific handler function. And that way you maintain a tight, strict separation between app logic and channel logic. I have just a few minutes left in my time. So I'm going to go ahead and look in chat for any questions while I kind of summarize what we've talked about so far. First is bridges or applications. They're a very high-level user-facing thing. In order to build them, we need reliable, safe, cross-chain communication. That turns out to be way more complicated than it sounds at first. We have to build out these header relays, we have to build out these off-chain actors, and it's very easy to mess up. And there are a lot of points where we can just fuck up and break the whole bridge. Excuse me. So specific hacks in the past have been, one, chain-specific logic leaking into the bridge. The minute you start doing like bespoke custom engineering for the chains you add, you're going to run into bugs about parsing and processing like Thorchain did. The logic that is chain specific needs to live on that chain, and the cross-chain parts should be completely chain agnostic. Standard message formats. So the other thing that we talked about is the poly network hack, where there was not a separation between the communication channel and the application. And the attacker was able to use the communication channel to get admin rights on the application. So the solution there is to have strict layers, is to force all contracts involved to explicitly denote which of their functions are cross-chain functions and which are local-only functions. And if we have good layering, we're going to prevent a lot of these issues. So I have no current questions in chat, so I'm going to go ahead and wrap up. Thanks for the time, everybody.
Thanks, James. This is great. So we're going to take a 2-minute break and then transition to the next talk. Thanks again. Oh,
No
also,
problem.
would you mind sharing your slides in the chat or on Twitter?
Yeah, I will do that after this.
Okay, perfect. Thank you.
Thanks.